In continuing on with our discussion and examples of basically solving linear dynamic systems with differential equation methods, we're going to look at page 18 and look at example 2 and basically see an overdamped case, and also how we're actually going to look at that overdamped case when we're looking at the derivative form of the differential equation. So basically taking KVL equation, expanding it by the current voltage characteristics, in which, because of series elements relationships, all the currents will be the same. But then we're actually going to basically put that equation into its second order differential equation form. So we're going to take a look at basically a 50 volt source that's connected to a 25 ohm resistor and a 3 Henry inductor, and at t equals 0 we're going to close that switch over to the right hand side, in which we're going to basically create a source-free series RLC circuit. Now, for this problem, we want to actually find IL of t for t greater than 0. So we're looking for the inductor current this time. But the inductor current is actually the same as the resistor current, and also the same for the capacitor's current. So let's take a look at the initial conditions for t less than 0, in which we find IL of 0 minus and VC of 0 minus as well. VC of 0 minus is obvious, because that capacitor wasn't connected to a source for t less than 0. That capacitor's initial voltage will just be 0 volts. But over here, it's very, very easy to find the inductor's current. The inductor's acting like a short circuit, because if the change in the current is 0, then the voltage is going to be 0. So therefore, we actually can easily find that inductor's current by 50 volts divided by 25 ohms, in which we get 2 amps. But we know that at t is equal to 0 plus, that VC of 0 minus is equal to VC of 0 plus. So VC of 0 plus will be held to 0 volts, because that voltage can instantaneously change. And IL of 0 minus will be equal to IL of 0 plus, basically rendering 2 amps, because that current also can't instantaneously change. But the other initial condition that we're going to need is basically going to be DIL of 0 plus dt, the change in that initial condition, and that's equal to VL of 0 plus divided by L. Now again, we get that from evaluating the current voltage characteristic of the inductor at t equals 0 plus. And that obviously makes sense, because this represents change right here, right? So represents change, and the only time we're going to start seeing change is once that switch has actually closed over to the other side. And I should have actually had, messed up a little bit. Switch should be right there. Yeah. So in this case, guys, we're going to have to go through and find VL of 0 plus. And the reason why we're going to have to find that is because that value can instantaneously change. The current through the inductor can't instantaneously change, but the voltage can instantaneously change. We're going to see something really, really interesting. So remember that when we're actually getting that inductor into a steady state, what's really happening is that magnetic field starts building and starts retarding that flow of current. And so once that magnetic field becomes stable and it's built to its full capacity, all current can just pass right through that. But the thing is that once that magnetic field actually starts breaking down, what happens is very, very unique. Basically, that current, it can't change direction, obviously. But what happens is that the voltage, as that magnetic field starts breaking down, it flips polarity. And so once we start seeing it flip polarity, then we may actually see a negative sign on that voltage across the capacitor for VL, across the inductor for VL of 0 plus. But because that can instantaneously change, the only way that we can find that is by evaluating the KVL equation at t is equal to 0 plus. So let's take a look at that. VL of 0 plus VR of 0 plus VC of 0 plus is obviously going to be equal to 0. Now, VL of 0 plus is exactly what we're looking to find. VC of 0 plus, since that can't instantaneously change, is going to be still held to 0 volts. But we now actually have a current that's going to flow into the 30 ohm resistor at t is equal to 0 plus, and that's going to drive a voltage across that at that instance in time. So R times IL of 0 plus, that's simply going to be 30 times 2 amps. And remember that the current direction is what drives basically that polarity. So staying consistent with KVL, VL of 0 plus 30 times 2 gives us 60. But we solve for VL of 0 plus, and sure enough, guys, VL of 0 plus is equal to negative 60 volts. So we have just proved mathematically that sure enough, once that magnetic field starts collapsing down, that we actually get a negative polarity for the voltage across that inductor. And that's exactly what we expected to see. So the change in that initial condition, that rate of change, amps per second that we're going to see here, DIL of 0 plus dt is equal to negative 60 volts over 3 henries. And that's equal to negative 20 amps per second. And this is a beautiful thing right here, because that's exactly what we would expect to see. The current's going to be dying off, that magnetic field is going to be dying, current's going to be released into that circuit, everything's going to burn up in terms of heat. So we actually expect to see a negative rate of change here, because we're actually going to see that current die off. All right, so now we got to derive the differential equation. And the first way that we're actually going to be concerning ourselves with evaluating evaluating the circuit is by finding the expansion of the initial KVL equation, and then we're going to take its derivative and see what we get. So, moving over to the next board. All right, here we go. We're going to derive the differential equation for t greater than 0, and we're going to put it into what I call its derivative form. So here, going around the closed loop, obviously ILT, we basically want to stay consistent with the way that current was initially basically was found at the beginning of the problem, and that can't change direction. So we're just going to basically allow that to flow basically counterclockwise here. So by KVL, VL of t plus VR of t plus VC of t is equal to 0 volts. And once we expand that by the current voltage characteristics, everything in that equation will be of the form of the inductor's current, because IL of t is equal to IR of t is equal to IC of t. So series elements have the same current. So L DIL of t dt plus R times IR of t plus 1 over C times the integral from 0 to t of IC tau d tau plus VC of 0 plus is equal to 0 volts. Now this is what we call the integral form right here. And we're actually going to go back and solve that at another point. But in order to get it into a second order differential equation, we're just going to simply take the derivative of this equation. Bam! Take its derivative right here. And once we do that, that first order, that DILT dt becomes d squared IT dt squared. I went ahead and took out the L and the R and the I in the subscripts because all the currents are the same. And then here, the derivative of I of t times R over L becomes R over L times DIT dt. Here, but we take the derivative of the integral, and that kills off that integral right there, and we get 1 over LC times I of t. Now obviously over here, that initial condition, that's a constant value. So when we take its derivative, bam, it goes away. So we don't even have to worry about it anymore. So now we have a differential equation that we're ready to solve. In standard form, obviously, d squared I of t dt squared plus 10 dit dt plus 9 times it is equal to 0. Now we're ready to take its Laplace transform. Take its Laplace transform going into the frequency domain, right? Frequency domain. So s squared I of s minus s times I of 0 plus minus I prime of 0 plus 10 times s times I of s minus I of 0 plus 9 times is, and that's equal to 0. So we solve for basically, well, we combine like variables of I of s, move all our initial conditions over to the right-hand side, get our characteristic equation right here, s squared plus 10s plus 9. And if we look right here, guys, here I prime of 0 plus, that's negative 20, right? So we get 10 times I naught, that's 10 times 2. These two cancel each other out. And the only thing that we're going to be left with on the right-hand side is 2s. So we solve for I of s, and sure enough, we get 2s over the factor polynomial of s squared plus 10s plus 9 is s plus 1 times s plus 9. Oh, we got real distinct roots right here. Guys, we have a overdamped case in which we have plenty of resistance to keep this thing from oscillating. So sure enough, easy to solve this, super easy to solve. By partial fraction expansion, we put it into its simple terms, a over s plus 1 plus b over s plus 9. And as we were seeing before, it's easy to go ahead and solve this because now we have one equation, basically two unknowns. So we need to actually find those coefficients of a and b. So we multiply through the left side, basically we multiply through by s plus 1 times s plus 9. And basically we get this equation to the form of 2s is equal to s plus 9a plus s plus 1b. Now we need basically two equations, two unknowns. Two unknowns is a and b. S is equal to 0, so that gives us 0 is equal to 9a plus b. S is equal to 1 gives us 2, which is equal to 10a plus b. Solve for a and b by basically putting those into our matrices and getting it into its row reduced echelon form. We get a is equal to negative 0.25, b is equal to 2.25. So finally, I of s in its true simple form is equal to negative 0.25 over s plus 1 plus 2.25 over s plus 9. I want to make sure you guys understand that this right here is still equal to 2s over s plus 1 over s plus 9, but these are expanded into its equivalent in simple terms. We take its inverse Laplace transform, and for t greater than 0, I of t, the total response, doesn't have a steady state condition other than 0 amps, is equal to negative 0.25 times e to the negative t plus 2.25 times e to the negative 9t amps. So that was how we actually solved basically a problem when we're looking for the current for series elements, but when we're considering an overdamped case in which we actually have real and distinct roots, but also basically finding that current in that derivative form. But what if we actually tried to find that, see if we actually could come up with the same form of I of s from the integral form? In the last video I said that those two would actually produce the same I of s current in the frequency domain. Well, let's kill two birds with one stone. Let's actually go back and revisit on page 22. We're going to revisit that integral form and see if we, in fact, we do come up with I of s is equal to 2s over s plus 1 over s plus 9. If they do, then we've actually proved that, sure enough, the integral form and the derivative form will actually produce the same exact frequency domain solution for I of s. Let's take a look all the way down here. So now looking at page 22. So page 22, we just go back and we're going to reconsider that integral form. So di of t dt plus 10 I of t plus 9 times the integral of 0 to t of I tau d tau plus vc of 0 plus divided by L is equal to 0. Let's take its Laplace transform directly. So Laplace transform, we get s times I of s minus I of 0 plus 10 times I of s. Now, with this integral, when we take its Laplace transform, we actually get 9 times I of s over s. And if we actually didn't have Vc of 0 plus as being 0 volts, we would actually have that value divided by L, also divided by s as well, because that would be basically the Laplace transform of constant is that constant divided by s. So, however, because Vc of 0 plus was equal to 0, we have 0 right here. But we got a problem. We got s in the denominator. We don't like that. We don't want that s in the denominator. So in order to actually solve this, we multiply both sides by s. And once we multiply both sides by s, oh, look at this. We get s squared times I of s minus s times I naught plus, and then plus 10s times is plus 9s. Oh man, so we take s times I naught, move it over to the other side, we get 2s over s plus 1 and s plus 9. We're going to continually kind of take a look at these types of problems, especially in our homework, and we're going to be continually proving that these two forms, the derivative form and the integral form, will still produce the same form of v of s or I of s. So now we've actually gone through the examples of the series elements you should be working on your homework right now. Now we're actually going to, in the next lecture, start looking at solving the parallel problems in those examples. So, see you then.